The W.M. Keck Foundation has awarded Michigan State University's Alad Harel and Marcus Dantos $1.3 million to start a new revolution in the way we use optical microscopes to understand the living world. The grant is one of 6 awarded nationally by the Keck Foundation in 2022 for science and engineering. This also marks the first time that scientists at MSU have claimed the award. The Keck Foundation encourages creativity by rewarding transformative projects that other funding agencies might see as too ambitious or risky.
Hi, I'm Marcus Dantos. I'm a distinguished professor at Michigan State University, and I work out of the Department of Chemistry, and I'm also an adjunct in the Department of Physics. Yeah, I work with lasers.
My name is Alad Harel. I'm an associate professor in the Department of Chemistry and also adjunct in physics, and my research spans ultra-fast science, or working with really short pulses of light, and working on all kinds of new techniques in molecular imaging.
Cool. Now, if you could each sort of just tell me a little bit of your background and what attracted you to MSU.
Since I was 10 years old, I decided that I wanted to be a scientist / inventor, and I thought that if one day I can have a lab and just invent stuff, that would be the best. And after my PhD and postdoc, I got an amazing offer from Michigan State University to build a big lab and have lasers and start inventing things. And I've been super happy ever since.
I love it. Alad, how about you?
I've also, since I was little, I always really liked, was attracted to science and math, and also kind of on the artistic side, I was really into photography, and so I entered lots of photography competitions, and I really wanted to do that. And then I kind of realized that how could I combine both of these loves, both science and art, and I realized it was a lot easier to be a scientist and do photography as a hobby than to be a photographer and do science as a hobby. So I thought, I could kind of go down this trajectory, and that's kind of what I've been following ever since. And I had an opportunity to come to MSU, and they said, we're going to give you this new lab and the opportunity to do whatever you want and change direction, go into really new areas, and you don't get that opportunity too often in your career. And so I jumped on it, and I've been very happy ever since.
So you've both started to talk about it, but tell me overall what your research interests are.
I have been working with ultra-short pulses since I started my PhD. And when I came to MSU, I started working on something called pulse shaping. So basically taking the very short pulse and making it, controlling it in ways that it gives it special properties in the time and the frequency domains. And my first foray into that was to apply it to a number of things like protein sequencing and biomedical imaging and standoff detection of explosives. Since then, I continue to do that, but more along the lines of, of how molecules behave under very intense laser fields, and people would think that they just simply explode, but we're finding that within a very, very short time, the time it takes to break one chemical bond, these molecules actually form new bonds, and people didn't think that with such amount of energy and during explosion you have times to form new bonds. And so that's been relatively cool, and we keep going in a number of directions.
Alad, how about you? Describe your research interests for us.
So my interests kind of span a wide range. I started off in my PhD working in an area called magnetic resonance. So if you're familiar with magnetic resonance imaging or MRIs that you would get in, say, a hospital. And so when I went to do my PhD, I met somebody who ended up being my advisor in that area, who just really inspired me because he was kind of doing things that I didn't even know existed. And so it was just a really inspirational kind of work. And he was an inspirational kind of guy, so I really gravitated towards that kind of research, and so that's kind of what I did in my PhD, was developing new methods in magnetic resonance imaging. And as I was nearing the end of my PhD and trying to decide what I was going to do, I thought, well, maybe I'll just continue in this field. But I realized I didn't have any really great ideas of what I wanted to do with that. So I thought, why don't I jump into a new field and see if I can apply those ideas from the MRI kind of community and apply it to the optical regime, where we work with light. And I've always been fascinated by working with light in one way or another, but I just didn't really have that opportunity. And so in my postdoc and subsequent to my PhD, that's really what I've worked on, is kind of merging these two very different areas, because they all have their own language, they have their own communities, their own history, and so on, their own physics. And so what I did in my independent career was really think about applying those kinds of ideas, and whether we could learn something new. And I got particularly interested in processes like photosynthesis, where plants have this incredible ability to take light and convert it to useful forms of energy, to chemical energy, store it as chemical energy. And how does that happen? And it turns out that happens on there are many, many time scales that happens on, and a lot of that's been understood for the last century or more. But the most fundamental kind of initial processes of photosynthesis are still not understood. And since they're not understood, we can't mimic them. We can't create artificial photosynthetic systems, which would be, really, of course, important for energy storage and utilization and alternative forms of energy. So I really got fascinated by that problem. And I thought, well, how does one measure these things that you can't see? They work on time scales that are millions of a billionth of a second. So you don't have a clock even that's fast enough to measure them. And that's where the idea of using really short pulses of light was intriguing. Can you use that as your clock? And what kind of processes can you see, that is, make movies of molecular processes, or how energy moves through molecules or through proteins? That was just captivating. And so that's kind of what we've been trying to do ever since, was make these movies, really actually see these things happen and catch them in time and space and in energy. And turned out that's a hard thing to do. And so you need to develop new tools to do that. The tools just don't exist. And so that's what we've been focused on.
I think this is a really remarkable achievement.
Douglas Gage is MSU's Vice President for Research and Innovation.
The Keck Foundation is a funder of scientific research, and they value one thing, I think, over anything else, and that's transformative innovation. They do not want to fund research that can be funded by any other agency, even the DARPA, or some of these sort of agencies that go for the really out there sort of research. So one of the things we had to do was really persuade Keck that this work was innovative, a little bit on the cutting edge, but not crazy enough that it would never work. And so that's a very fine balance between, what is possible, maybe challenging, but possible to achieve, but yet remains innovative enough that another agency might say, oh yeah, well, we'll take a chance on this one. So it's a very fine line. We submit Keck proposals every year. We've had some really out there sort of research projects, and we usually submit the grants with comments from failed grant applications, maybe to the NIH or NSF, with comments like, this sounds like science fiction, but if it works, it would be fantastic. Something like that. So you really have to persuade the reviewers at Keck, and it's a family foundation. Ultimately, they have experts that they bring in to really evaluate the science. But, they really want to make transformative change. And so it's a remarkable foundation. One of the things that it does for MSU is that it really validates the innovation that we have going on at the university. And we know that, but it's great to have a national organization really validate what we know about MSU. We're very grateful for this proposal, that it was funded. We're very grateful for this award. I'm convinced that the work that Elad and Marcos will do will indeed be transformational. If they can do the imaging of living systems at the resolution that they propose, that will be remarkable, and it will be indeed transformational. The innovation here comes from two very independently innovative scientists bringing together their ideas in really a novel way. And I think that's often the seed that leads to innovation. We try to promote that at MSU, and it's so we're looking forward to the outcome of this research, and I think it's going to be something to watch.
Well, let's talk about the prestigious and cool Keck Award you two have received. Sort of, how did you come together, and what are you going to work on in that project?
Basically, for the idea, a lad came to me and he said, I have this very interesting idea. I've been thinking over it for some time, and maybe we can work together. Maybe we can find a foundation that will fund this kind of very high impact but high risk project. And then I'll pass it to a lad to describe more. It was not the first shot.
Yeah, and this kind of comes back to what I was saying about the power of looking at combining different fields, coming at things from different perspectives, because people have come up with all kinds of ingenious ideas in astronomy and biology and all kinds of different realms of physics and engineering. And being aware of what people had done was really brought up a lot of challenges to me about how we could apply, are there optical analogs of these different types of methods? And so MRI always kind of came back to that idea of magnetic resonance imaging, where we form these beautiful images inside the human body. It's kind of a absolutely remarkable technology. And, the invention of MRI has a very interesting history. It goes back, it started off really in physics and looking at molecular beams and doing kind of this very specialized branch of physics. And then it moved into chemistry, where it could be used for identifying molecules and looking at proteins. And then it kind of moved into medicine. Medicine said, well, wait a second, we could also utilize this in some way. And, it kind of evolved in that way over a span of many decades to what we have today. But what always captivated me about magnetic resonance imaging was the fact that its resolution was really remarkable, because it used radio waves. And radio waves, they're great for transmitting sound, right? They're great for detecting if there's an airplane in the air via radar. But, they're very long wavelengths. So they're not really something you would think that would be good for high resolution imaging. And yet in magnetic resonance imaging, you routinely achieve resolution much smaller than that wavelength. So how does that happen? And so I started thinking about, was there a way to do that in optics? And so that was kind of brewing in the back of my mind for a long time, but it was something that would take such an enormous effort to even test. It didn't really make sense to apply to a traditional funding type of agency to do that. They just wouldn't be very interested without some results. And that's kind of where I thought, this kind of stuff Marcos does was so intriguing and could be so beneficial, because in the magnetic resonance imaging community, a lot of the manipulation of electromagnetic fields, now radio fields, can be done kind of at the click of a button. Right? It's all electronics. And in optics, that's not really the case. You have to pass light around from one mirror to another. It's like very complicated. But the stuff that Marcos developed was really was able to shape the light in ways that was very similar to the kind of shaping that had been done 50 years ago using electronics of these radio frequency electromagnetic waves. And so it made sense in terms of the timing, where the technology had matured, in order for us to take that and say, hey, can we do this now? Can we control these optical fields in ways that have not been achieved before, or maybe even attempted before? And so that's why I think this kind of partnership made so much sense. Even though we're both experts in lasers and ultrafast optics, it really made sense to kind of capitalize on our various expertise in order to for this Keck Foundation grant.
I know you're both true scientists, and you'll find what you find, but are there things you're hoping to find or questions you hope to answer?
Well, I think we should start with the stated goal, right? we all know about cells, and we know a lot about the organelles in the cells and how cells divide and so on. It's just fascinating. But most of what we know, let's divide. Let's say as follows: most of what we know about cells, either we can see on a regular light microscope, and in that case, we can see everything in motion, and then we can freeze and do electron microscopy, and then we can find, what is the shape of the different organelles, and then we can maybe crystallize the different proteins, and then we can know it at the atomic level. However, a lot of this, let's call it the biological machinery, is operating at length scales that are shorter than a wavelength. And so if we wanted to see how a protein is being made, well, there's no way right now. So we need to resort to methods that are either X-ray diffraction or electron microscopy. And with that, we take static images. And maybe by putting many, many millions of static images, we can begin to get an idea of how this might be happening in real life, right, or in motion. Our key goal here is, can we see the machinery of life in action with a resolution of nanometers? And that would be, thousands of millions of a meter. I mean, it's really, really tiny length scales. I mean, in most of the cases, our microscope will not look at a space much larger than the width of a hair. Most of the time, we're going to be way, way below that. And so we want, our main goal is resolution in the nanometer scale and time resolution. Can we get video rate, or maybe 10 or 100 times faster than video rate? If we get there, we both will be so excited. We'll be jumping up and down. And I think a lot of our colleagues will be equally excited.
Yeah, I think the challenge has been, as Marcos described, right, is that we tend to think that we can see these molecular machines. We can watch them in motion, right? And the truth is we can't. What we can see are these kind of static snapshots. So, and we're very good at inferring what happens from those static snapshots. So it's like, if you saw if you see a picture, you can infer a lot of maybe what's going on in the picture. But if you see a picture only, every hour, you're really missing a lot of the details of what's happening in between. How are people communicating? What is happening? What's the social structure? What's happening in that scene? And that's kind of where we are. We're very good at inferring, and we have people, enormous ingenuity has gone into figuring out the mechanisms of various biological processes. But it's a very, very slow discovery process, because every kind of science that one does is only revealing a very small, narrow window into that process. And by combining enough little snapshots of information, we can kind of piece together or we can form a hypothesis of what's happening. But that's really different than being able to observe it directly at the time scales that matter. And that's kind of the challenge that we're trying to, there are different technologies for getting those kind of snapshots. What the technology that does not exist now, and what's specifically addressed in this Keck Foundation grant, is how do we make these movies at the requisite time and spatial resolution to see directly what's happening, and to just accelerate that discovery process, because we are, after all, very visual. Where human beings are just visual. We understand things through how we see it. And so that's still a very large missing piece. So I think it's not just that we'll be excited to see, better resolution. I mean, there's always a goal of improving resolution and so on, but it's really to help aid our fundamental understanding of these complex processes, and so that we can advance science in general in ways just like light microscopy has advanced science 100 years ago. The advent of even more than hundreds of years ago, the advent of microscopy, light microscopy, really accelerated the knowledge of the microscopic world. And so that's the same kind of goal here. Just like astronomy is, with the more powerful telescopes, is accelerating the discovery of the planets and the evolution of the cosmos and so on. We would like to apply that to the kind of nanoscopic world, the world in which molecules and proteins and cells live.
As you move forward, both some challenges and some opportunities for the project.
Well, the biggest challenge is that we intend to use visible light. And visible light has a certain wavelength, which is about half a micron. And so there is the so-called diffraction limit that tells that you cannot resolve elements that are smaller than half of the wavelength. And so that's the number one challenge. As Elad was saying, we're going to be using ideas that are borrowed from magnetic resonance imaging. But that's the first challenge, right? It's like, who do we think we are that we can break the diffraction limit? Now, there was, not too long ago, a Nobel Prize for 3 amazing scientists that figured out approaches to break the diffraction limit by using, a number of different approaches and methods that primarily depend on fluorescence and multiply exciting molecules. And we think we have a new idea on how to do this. And if we are successful, we are predicting that our method will be more, let's say, less detrimental to molecules, and will allow us to image with a very high speed, entire movies, so that we can see this biology of life again. I'll repeat, in motion, and so that's the biggest challenge that I see.
Yeah, I think as Marcos said, we have to kind of start with the most basic premise of the entire proposal, which is just distinguishing two objects that are really close by to one another, closer than what the kind of traditional limits impose, and then the question is, how do you extrapolate from that to, say, 2 dimensions or 3 dimensions or more complicated imaging scenarios? So we really have to do some really basic research in terms of just showing what are the limits. And, the real life limits are dictated by things like the sensitivity of the measurement, right? You don't have infinite sensitivity. You're always limited in some way of how faint of a signal that you can isolate in the background of all kinds of other interfering signals. So there are questions about how many photons can you collect and so on. There are questions about what type of samples would be appropriate, right? Do we start off with samples that we can manufacture and then we know all their spatial and temporal properties, and then we eventually want to move to samples that are soft matter, right? Biological samples. How much light can they handle before they start to break down? So what is the kind of contrast that we expect to see in these kinds of images, right? At the end of the day, it's all about contrast, distinguishing one thing from another. And so is there going to be a strong contrast between one type of protein and another type, or one organelle and another type? So we have to kind of pose those types of questions. And all of these questions will involve both the kind of fundamental basic research that we're planning on doing, but also collaborations with other folks at MSU and elsewhere who can really provide us the right kinds of samples and who can help us formulate the questions in the right way. That is, what are the important questions? Why do we need this kind of resolution? Under what circumstances is it important? Under what circumstances is it not important? So we want to capitalize, take advantage of the expertise that people have developed over decades on various specific problems that they've been focused on, and how our technique could be applied to that. So just like the introduction of any new technique, whether it was going back to the MRI example, at first, the first MRI experiments were distinguishing 2 tubes of water. That's not terribly interesting. But someone said, wait a second, the brain is just a bunch of compartments of water. So can we extrapolate to that? And what kind of contrast would we see in the brain or in the body? And under what circumstances do we need to enhance that contrast? Or what kind of different pulse sequences can we use to see one feature and not another? So there was decades and decades of work to get to where we are today, where that can be used as a diagnostic tool. and as a routine tool that doctors who are not specialists in the technology of MRI can use to make medical decisions, right? And so that's going to be the same thing here, where we have to prove that these techniques are going to give information that's useful and not distorted in some way, or at least that we know what the distortions are, so that we can expect them and we can account for them. So there's a lot of work just to be done in the verification step, because we don't know what we're going to see exactly, but which is what makes it exciting. But also we have to appreciate that fact.
As we start the first experiments, which will be on very small particles that are inert and static, but as soon as we can demonstrate that this approach works in one dimension, we already know exactly how to take it to 2 dimensions, and it will already have a huge impact. We just, our brains are now focused on getting that first step done.
Well, Marcos and Alad, thank you for telling me about this great project. Just summarize what you'd like us to know about it as it gets started.
As scientists, we're always greatly appreciative of the fact that these external sources, these philanthropic sources or funding sources or wherever they may be, really kind of appreciate the challenges that we have to face as scientists, the kind of challenges in the infrastructure that we need and the resource that we need to really test out new ideas. So it's very gratifying, and we're extremely appreciative of the fact that we're given that opportunity, that the agency, that the Keck Foundation in this case, knows and understands the kind of challenges that and the kind of risks that one has to take sometimes in order to make breakthrough discoveries. And so just as scientists, we're incredibly lucky that we get to have that chance. That doesn't come along terribly often. And we think that something really good is going to come out of this. We believe that something really good is going to come out of this, and it's going to push science in one way or another forward. And so, we really do thank the Keck Foundation, and we thank MSU as well for really being supportive of us and of the application and of the process to put forward the best application we could, and to really be highly competitive with many, many other universities and very strong groups applying for this as well.
Yeah, I would like to say, just like Alad, it's really wonderful that there are these foundations like the Keck Foundation that recognizes that traditional funding sources, let's say all the federal agencies, first of all, have limited funds, and also, they require a much higher level of proof before they will fund a particular endeavor. And in this case, we're really proposing something that has never been proposed, as far as we know. It has never been shown, and so it poses a high risk but high reward type of activity. And it's wonderful that there are institutions like the Keck Foundation that are saying, if some scientists convince us that there is a possibility to achieve results that have never been observed before that could have a tremendous impact in science, we would like to facilitate that. And that's really fantastic. And as Alad said, to be on the receiving end is just incredible. It's just a wonderful opportunity, and one that we want to do the most for.
Well, gentlemen, congratulations again on earning this prestigious award from the Keck Foundation, and all the best moving forward.
Thank you.
Okay, thank you.
That was Marcus Dantos, an MSU Foundation professor and a University Distinguished Professor of Chemistry in the College of Natural Science, and Alad Harrell, an Associate Professor in the Department of Chemistry. And I'm Russ White. This is MSU Today.